Good morning, everybody, and welcome back to Next Door NetAdmin. When people ask me, what do you do for a living? What's your job? If I say I work in IT, which is honestly what I usually say, a lot of the times, the very next question is, oh, so like you're a computer programmer? And my answer to that is usually, no, I am not. And I explain a little bit more about what I do as a network admin, as a network engineer. But am I a programmer? Then I start getting into the caveats as well. I program routers and switches. That's part of what I do. Some of them are, point and click ones. I wouldn't call that programming. But there are others that are more enterprise grade, Cisco Catalysts or other routers, ASRs, etc., that do have a command line programming language of their own. And those I would say that I program. Okay, more caveats. Well, I do write code sometimes for specific purposes. And I some of them can be over 1,000 lines long, and people would kind of look at that and go, well, it sounds like you're programming. And I would go, but I'm not, because it's not a programming language, it's more scripting. So what's the difference? What's the difference between programming something or writing a script? What's the difference? Why do we draw the distinction? Let's talk about it. A programming language can be ranked by how abstracted it is. At the very basic level, you've got machine language. Machine language is the sequence of zeros and ones, literally zeros and ones, that you feed to a CPU in order to make it do a thing. One step above that, you have assembly language. Assembly language is a series of very, very, very low-level instructions that get translated into machine language by a specialized program called a compiler. Assembly language works very much on the level of the CPU has a certain number of registers. Think of them as very, very small pieces of memory that are directly available to the CPU. There's typically only like 8 or 16 of these, and they typically hold anywhere from 8 bits to maybe 64. It's been like 20 years since I've done any assembly programming, so I'm sure some things have changed. But it's very, very specific. Go to memory, fetch this piece of information, put it in this register. Now I want you to operate on it by adding it to a value in this register, or subtracting it, or multiplying it, or whatever you want to do with it. But it is on that level of I can only operate on a certain, 2, maybe 4 bytes of data at a time. If I want anything else, I'm going to have to tell it to go out to memory and fetch that. If I want to modify anything else the CPU is doing, I can. This is assembly language. I have direct control of the hardware. That is a very tricky thing to program in, because you have to think very much on the level of the computer. You are directly controlling the hardware with the instructions you give it. So if you tell it to do a thing that it can't do, it's not going to work. Worse, you at best, your compiler might reject it and tell you this isn't something that I can translate correctly. At worst, you could end up discovering the next halt and catch fire instruction. Something that just stops the system in its tracks, and the only way to recover it is by rebooting. Which is not a great thing. But There's a lot of fun HCFs that I could get into, but not right now. As you go higher, you get to higher level languages that still have direct control of some of the memory and hardware. I say direct control. It's not direct, but you can write instructions that do physically affect the machine. I'm thinking of languages like C or some of the derivatives thereof, where you can go, I want to allocate a section of memory. I want it to be at these addresses in RAM. I want to do this, I want to do that. And then when I'm done with it, I'm going to manually instruct the computer to clean it up, free this range of memory, make it available to other programs. And if you don't, then that memory remains forever allocated to that program. And over time, your system runs out of available memory. It's where we got the term memory leak, is for programs like this that manually have to request and then manually free up the memory. Freeing up the memory was something that occasionally got forgotten, maybe because you held on to it and you thought you were going to go back and do something more with the data, but your program never actually did so, and you either forgot about it or it was overlooked or whatever, and you get a memory leak. Go higher up the stack again, you get to even higher languages like Java or Python or other languages like that that don't have direct control of the memory. In something like Java, you say, I want a variable. I don't get to specify where in memory, what addresses I want to put it at. I don't get to directly tell it to, hey, I'm done with this. Now I'd like you to clean it up. Java doesn't have that as a concept. In Java specifically, there's something called the garbage collector. It's a background part of the Java process that goes around and says, you're not using this anymore, and either the program's finished or I can tell that we're not coming back to this, so I'm going to clean it up and make the memory available again. Cool. That is a feature of a higher level programming language that is not necessarily available in a lower level language where you're doing a lot of this manually and actually telling the computer how you want it to work. Cool. I mentioned that in assembly you have something called a compiler that takes the instructions and compiles it down into machine language, actual instructions that are sent to the CPU. The same is true for some of these intermediate level languages and for some of the higher level languages too. Something like C also needs a compiler to compile the instructions down. One of the caveats with compiled software is because it's being brought down to the level of actual instructions for actual hardware, it's specific to that hardware. You can't take something that is compiled for a 64-bit processor where it's working with 64 bits and all the various widths available. You cannot take that and run it directly on a 32-bit processor. It doesn't know what to do with it. All of its internal processes are 32-bit, not 64-bit. You hand it to the processor and it goes, I don't even. What is this? And that will lead to problems. Because it's already been compiled, your compiler will not catch that. You'll just end up with something that doesn't run, or it crashes when you try. So for compiled languages, you very deliberately have to go, okay, what am I compiling this for? Am I compiling this for x64? Am I compiling this for ARM64? Am I compiling this for PowerPC, one of the old Macintosh systems? Am I compiling this for newer Macs with the M1 or the M2 or higher? What am I compiling this software for? x64 is a good default because that's what we're all using for the most part these days, at least in the PC and Linux world. But there's still other architectures out there. And if you want to make your software work on those architectures, you have to manually compile it to do so. On the other hand, you have interpreted languages. Interpreted languages have their own command interpreter, something like PHP, for example. PHP itself, the engine, may need to be compiled for different architectures. But once you have the engine in place, you can just feed it a PHP program and it will execute that program. That program is portable. You can move it from PC to PC no matter what architecture it is, as long as you have a PHP engine installed for that architecture, it will work. Something like Java kind of sits in the middle of this. Java is a little odd, I would say, in that you do have to compile it, but it does not compile it to native machine code. You compile it to bytecode, which is something that the Java virtual machine on any given PC will take, interpret, and spit out native instructions basically on the fly, something called just-in-time compilation. It's a separate approach. You're still partially compiling it, but then the compiled bytecode is supposed to be portable and you can take that anywhere. Okay, fine. These are all programming languages, some of which I've worked with. I've worked with assembly, I've worked with Java, I've worked with PHP, I've looked at C. I have not learned C, so that's not a thing. But you can do a lot of very powerful things with this. What I do a lot more of, however, is scripting. In some ways, scripting looks and acts in a very similar way to a programmed language. You're entering a sequence of instructions, and when the computer runs that sequence of instructions, you get a result. Hopefully you get the desired result, but you get a result. So what's the difference? Why do we distinguish between a programming language and a scripting language? I can't tell you the exact dictionary definition of the difference here, but I can tell you what the difference is to me. To me, the main difference is that a programming language is something that is not in of itself something that you can type into the machine and have it achieve the expected result. If I allocate a variable, if I want to say, okay, set aside this range of memory, etc., etc., I don't have anything on the computer that can tell it to do that. If I want to tell it, okay, read the position from the mouse, I don't have anything that can do that specifically. I have to have a compiler that compiles the instruction down and tells it, okay, go to this hardware device, look at this range of addresses, read the position, feed it back to me, put it in this variable. Okay. And so it's very hardware specific, and it's not something that I can just open a command prompt, type in a command, and off we go. But a scripted language is. A scripted language should be, in my mind, a sequence of instructions, commands, that you could type into a command shell, keyword there, command shell, and actually have a result. So that's things like bash. In the Linux world, bash is the born-again shell. There are lots of other shells out there. I'm not bash specific, but bash is what I use most often. There's dash, the Debian-Almquist shell. There's just regular sh, if you want the lowest level. There's CSH, there's ZSH, there's lots of different shells available. And I'm not meaning to pick and choose favorites. On the Windows side, you have the command prompt, CMD. That's the first command shell that anybody's going to think of. But more and more, since the days of 2008 R2, Windows has also been bringing PowerShell into the greater production. I was going to say into the world, but into greater production, shall we say. PowerShell, the idea of it is most often encountered in Windows, but the actual idea of it was to write a command interpreter, a command shell that could run anywhere. Linux, Mac, Windows, anywhere, so long as you had a command interpreter for that language. And in that respect, it behaves a lot more like an interpreted programming language. Yes, absolutely. Within Windows, I consider it a command shell because it was intended and explicitly set up to replicate the look and feel of command prompt. The general idea was over time, more and more things would become PowerShell, and command prompt would be one of those archaic legacy things that nobody has to touch anymore because we've got something better now. I have seen no evidence of command prompt disappearing because it's frankly too useful, particularly when you want a lower level interface that doesn't have all of the extra trappings and complexity of PowerShell. But they're both intended, in my mind at least, to be command shells, which means that I can take a PowerShell script or a bash script or a command script, open up the particular shell environment that it's designed to work with, and I can go through and type in one command at a time, and I will get to the desired endpoint. I'm going to detour for just a second here. When I was working at a co-op job in university, for a little while, I had a job with a bank development center, a place where they wrote the next version of the bank's internal software. They had server guys. They had desktop guys. I was attached to the desktop team. They had server guys who were in charge of the servers. And pretty much the only thing I did with the servers was go down and rotate the backup tapes on a daily basis, which was fun, don't get me wrong. I enjoyed that. But one of the things that the server guys asked me was, can you script? And at the time I went, I don't know. What do you mean? Like, is that programming? And they went, okay. A good system administrator only does a task once. And then he writes a script to do it for him forever after that. This was advice that was passed down to me by other experienced system administrators. Do I do this? No, I really don't. For a lot of things, I've found that if it's something that you do very infrequently, I only have to touch this once a year, once every 3 years, once every 6 months. And it only takes like 2 minutes. Okay. Is it worth my time to sink an hour into writing and testing a script to do this particular task? If it only takes me 2 minutes every 6 months, it's going to take me 15 years before I recoup the time that I spent if I spent an hour to write a script. Is it worth it? Not for that. But if you look at something and go, this is going to take 5 to 10 minutes of effort for every single time we do this task. We do it 4 or 5 times a week. And if it's not done by an expert then everything breaks, and then the expert, me in this case, has to be brought in order to do it right. Okay, that is easily an hour's worth of work per week. That's 50 hours of work a year. And it has to be done by a particular person. It can't be done by other people. This is where a script becomes a really important thing. If you can break down the sequence of steps that you go through, and you can find a way for the computer to do all the thinking that goes, oh, is this condition true? Is this condition true? If I have to encounter several error conditions, how do I work through them step by step? If you can do the thinking ahead of time and plan it all out, then a script is super useful because it's just a sequence of commands executed one after another. And if you test it, it may take you an awful lot of time to write and test a complicated script. The script I'm thinking of at this point is one that creates new user accounts for a particular client. It's a complex environment. It uses tools that are not in use at any of our other clients. So it's not something that my coworkers on help desk are familiar with. It's familiar enough to me because I'm the one who set that environment up. But if I want other people to be able to create user accounts, do it without errors for the most part, and we're doing 3, 4, 5 of these a week, it's worth it to write a script. Because like I said, if it's taking an hour of work to do it manually per week, that's 50 weeks in a year. I can spend literally an entire weekend writing this script, and it's still a better use of our time collectively than trying to teach people to do it all manually every single time without errors. And this is what I did. I wrote a script. It was 1,200 plus lines of code. I did it over a weekend and then, tweaked it, tested it, and made slight revisions to it until it works 98% of the time pretty flawlessly. That's not to toot my own horn. That's to say that this is something that actually saved a lot of time and effort and allowed other people to perform the same tasks without as many errors. That is the point of a script. And I also find that a script is really accessible. Anybody who opens that script can see the actual commands that are being executed. They can say, oh, you're testing for this condition, you're testing for this condition, and when you find what you're looking for, this is the command you execute. Anybody could go back through, open up a PowerShell terminal, and they could paste those lines of code in there. They could review it, see for themselves what it did, and verify that there was nothing hinky going on there. There's no buried commands that try and fetch data out of the system and send it back to me somewhere. You can see what it's doing. And even more so, you can copy and paste it yourself and make sure that you know what you're running before you do it. Scripts are therefore very useful not only for making sure that you can accomplish a task and make that available to other people to accomplish the task, they're also really, really useful for learning. Open a script, read through it, practice it yourself, test a few of the commands in isolation. If I do this, what happens? Oh, this is what happens. And I see how this now works with the rest of the system. And that's kind of the difference between programming and scripting. In a program, I can't see what the original commands are. The only thing that I do is make sure that I'm downloading the right version of the program for the architecture that I'm running on. And beyond that, it does what it does. And there's nothing that I can do about it to change the code. most of the time. We're not talking open source here. We're just talking about when you have the compiled code and that's all you have. With a script, I can look at it and go, this isn't going to work correctly in my environment, but if I change it just a little bit, I might get the desired result. I can read through it, I can learn it, I can review the code, and anybody else who reads one of my scripts can also learn it and figure out what's going on. So, do I consider myself a programmer? No, not so much. But I do write scripts because I am a network administrator. And there are times when you do it a few times and you realize, I should write something to do this for me. For everybody. Not just me, but for everybody else who's going to do it too. So that's what I've got for you today. Hopefully you enjoyed that. I am your next door NetAdmin, and we'll see you next time.